Hello everyone, and welcome to my attempts to show you more clearly how it is that we can balance out the reaction equation for the reaction between sodium bicarbonate and calcium chloride. You can see sodium bicarbonate right back there, the NaHCO looking formula. There's our calcium chloride. Didn't have a calcium, so we used the magnesium because they're on the same row in the periodic table, the same, same family, so same number of valence electrons, so that'll be calcium for today. So we've got our reactants, the things that are going to react and did react in this reaction, okay? And then over here, we've got labels for the products, including the mystery substance, the precipitate. So I want to show you another way that you could kind of figure out what that precipitant exactly is, okay? So we know that we did a flame test to test for carbon dioxide. So that molecule is solid. We know that all of these atoms in these three molecules, two different molecules, three in total, that they're going to break apart from these molecules and recombine to form new substances. That's what happens in a chemical reaction. And we did capture one of the gases that came from that chemical reaction. So what happened in the reaction is one of these sodium bicarbonates got pulled apart, and two of the carbon atoms and one carbon atom and two oxygen atoms, separate themselves, and then they bond up as shown. Maybe not shown clearly, but you know, I'm not a professional chemist, I just play one on TV. So we should have a double bond there and there, and we should have a double bond here and here. A little crossover-ish. But there's our carbon dioxide. Okay? So that's one product of this process is carbon dioxide, okay? It gets produced. So right there, you know you've got a chemical reaction because you made a new substance, okay? But we want to account for everything, okay? And we also want to find out what this mystery substance is going to be that we just don't know yet. So carbon dioxide is one of the molecules that got formed. Beautiful. In the test tube, and we did that through the flame test, of course, you'll recall. In the test tube, we were able to collect a certain volume. Can I get this in the shot? There we go. Oh. It's my lens. There we are. There we are. We were able to get some salt water, right? So using, just like we did in electrolysis, right, where we found out how much hydrogen and oxygen we should get from the formula, because the formula said we should get twice as much hydrogen as oxygen, so did the chemical equation. Well, we can figure out how much of the salt water we should have got, okay? It's very simple measurements. We won't go over it now, but we find out that we have one molecule of salt for every two molecules of salt for every one molecule of water that was in that test tube of salt water, okay? It's a very thick solution, so you use double the amount of sodium chloride. Makes sense? All right, so one of the sodiums from our reactants gets pulled out and forms with a chlorine, and that's an ionic bond, which means sodium just gives away an electron, it doesn't receive one, okay? So there's one NaCl, and if I can put that back on camera for you a little bit better, there we go. There's one NaCl, and right here, we will put our second NaCl, so I'll just make another one of those, ionic bond, there we go. And not on screen, now appearing on screen, NaCl. Beautiful. Okay, so now we've got most of the products of this reaction taken care of, okay? What we don't really have, though, is we don't have the mystery material. That's what we got to figure out what it is, okay? So now there's a whole bunch of leftover stuff, and maybe the whole bunch of leftover stuff is what actually makes up our, except for one thing, always double check your work, right? So I was going for the mystery, right? But then I look over here. We still have that H2O to deal with, don't we? H2O, okay. So I was looking over here and I'm like, looks like a lot of hydrogens left. That doesn't seem quite right. It wasn't. So I double checked my work and I found out that I'm missing a water molecule. There we go. We'll put that there so you can see it a little bit better. There you are. All right, so here's water right there. Cool, cool. Okay, so we got a sodium chloride there, a sodium chloride there. One water, 1 carbon dioxide, and that's what the formula calls for, okay? Now there's the mystery. So the mystery might be made up of all the stuff that we have left, but maybe it belongs in some of these molecules, except that we tested specifically for carbon dioxide and found it, okay? So we can't add any of these other elements to that because that makes it a new molecule and it wouldn't have flame tested the same. So carbon dioxide is solid. We're putting that down. That's what we got. It's good, okay? Water, the same thing. Easy to test for salt water. You boil away the water, collect it through tubes, collect it in a beaker, and now you know that your water is pure water. That's easy enough to do, and scientists have done it. And what gets left behind when you boil away salt water is salt. And you can look at the volume of the salt, compare it to the volume of water you boiled away, and you can see that for every 1 molecule of water, 2 molecules of salt were left behind. So that's very testable and very determinable, okay? So none of this stuff is going to get messed with. It looks like all of the piles of extra elements that came from our reactants don't belong to any of these molecules, which only leaves us one conclusion. They belong to a molecule of their own. So again, this is playing the role of magnesium, again, because we don't have a calcium, but magnesium is its closest relative on the periodic table, has 2 valence electrons, just like calcium. So I'm just substituting magnesium, okay? So here's what we're using for calcium. Here's a carbon, so that can link up there. And then you've got 3 valence electrons that need to be filled, and you've got 3 oxygen atoms. So that seems like a pretty easy double bond connection. So I can do that there, I can do this here. And here's my third. I'm sorry, I realize I'm doing this off camera for you. It's hard to tell where the camera can see. So basically there I am, sorry. So here's my calcium. I bonded it to my carbon, which was left over. And then I can bond the oxygen to that, another oxygen to that. And then I can finish the chain by doing a double bond here. And a double bond, single bond there. Hold on. Nope, wrong. Double bond there. Bond there. And there we are. All right, so now we have in this molecule CaCO3. Everything got used. There's nothing left over where we had our reactants. All the atoms of every element, put that in sight for you, there you go. All the elements of every atom of every element is shown here. They all recombined in a different way to make, let me move this aside, a different new substances, okay? We didn't start with any of this stuff, but this is all the stuff that we ended up with, okay? So to carry this out, right, all these other things are already in your formula. So this new molecule, which you may not have had in your formula, is, as we take a look at it, where can I put this? Can it be seen? Let's push this back. This new molecule right here is CaCO3. That is also known as chalk, like old blackboard chalk. It's found in antacids like Tums and stuff like that. Calcium carbonate helps to absorb stomach acids and things like that. So there it is. That's how the equation could have been balanced out. I know I showed you in class. How the equation would get balanced out on paper using chemical formulas and subscripts and coefficients and all that stuff. But there's no reason why you can't do it out with models like this. And you could even draw little pieces of paper for each little one, each atom of each element if you wanted to, and just shuffle them around that way. But that's really what this is. Like I said before, it's like playing with Legos. You're given a certain amount of Legos, a certain amount of pieces of certain types and certain shapes, and you can put them together in all kinds of different combinations as long as you use the same Legos and you don't lose any. And that's keeping with the law of conservation of mass. And that's exactly what we did. If this didn't work, if I couldn't make these molecules, there would have been leftover atoms here. Okay? But there weren't any leftover atoms. And all the molecules we made are testable. We may not have tested them all in class, but it's very easy to perform tests on salt. Separate salt from water and find out how much water you should have had and how much salt you should have had. And that tells you that those two terms in the equation are correct. They're the correct molecules and the correct coefficients, 2 NaCl, 1 H2O. Okay, same thing with over here. We've got 1 calcium carbonate, okay, and 1 carbon dioxide. So these are all testable. We tested the carbon dioxide with a flame test. We can look at the amount of carbon dioxide in the test tubes and say this is the correct amount of carbon dioxide that would have formed if all these other molecules formed. Same thing for that. Okay, you can test the calcium carbonate with all kinds of chemical tests. But the main point of this is that we were able to identify a missing molecule by balancing out equations and testing for these other substances, so we were sure that these molecules were correct. Okay? And then what you got left over is probably going to make up your molecule one way or the other. And figuring that out beyond, in a more complicated way than what we did today is for higher level chemistry. But if you have to, after having seen me balance the equation for this lab on the board and seeing this demonstration, if you think you pretty much get the gist of it, I'd say you're in good shape. So I hope this helps, and thanks for tuning in. Thanks, and apologies for putting up for the subpar cinematography, but I'm learning. Take care, everybody. See ya.